In this video, we will discuss batteries. Batteries are composed of electrochemical cells. So in these electrochemical cells, you have a reaction occurring which produces electrons, and that is therefore your battery. So in this example, we have a zinc copper cell where we have zinc here, which is classed as the anode. And this zinc is sitting in a zinc sulfate solution. So what happens is the zinc slowly dissolves into this solution. So you get zinc ions produced. So zinc 2+. And the charge, so this is positively charged. This means it's lost electrons, and these electrons flow through this path here, through whatever load you want to drive your current through, to the copper electrode on this side. And the copper electrode sits in a copper sulfate solution. So when these electrons are then present at this side, you get copper ions that are in the solution taking these electrons and plating themselves to this copper electrode. So you have electrons flowing around here, and what you have in the solution is a buildup of zinc ions here and a depletion of copper ions here. What that does is gives you an imbalance in ions, so you get SO4 ions, or an ion imbalance in SO4 ions, and these then flow through this porous membrane to balance the charge on this side. So that's how a cell works. For those with a background in chemistry, you'll notice this is classed as plus and this is classed as minus, because electrons flow in this direction and we class current in this direction. So we class in current as going from plus to minus. But the plus we have called the cathode here. So for those with a background in chemistry, you might find this a bit strange. If I just escape this and have a look at a Wikipedia page, what we have here is electroplating. So we have a battery here. We have a battery up here. And that's producing electrons on this side, on this electrode. And what you're getting in electroplating is this copper dissolving, the copper ions going across here and then reacting with these electrons to then copper plate this electrode. So the copper plating is occurring at the cathode side because the copper ions are reacting with these electrons. So this is electroplating, and you see a battery is used to produce this effect. In our case, we are making a battery, so this is our actually battery, but because the copper is being plated on this electrode, this is known as the cathode side, although it is positive in this case. Okay, so that's just, it seems to be a little bit of ambiguity, what you call an anode and cathode, but it is different when you're talking about batteries compared to things like electroplating. In terms of terminology of a battery, we have these different characteristics. We have the battery's capacity, and the capacity is the amount of energy it's stored, and it's quoted usually in milliamp hours. So if you have 1000 milliamp hours, that means you can produce 1 amp of current for 1 hour with that battery. The C rate corresponds to how quickly you can discharge that battery, or how much current you can get from that battery. And it's defined as the current you can take as a function of the capacity of the battery. You do have to be careful drawing current from a battery, because if you exceed this C rate, then the battery can overheat and explode. The density, or the energy density, can be given in terms of a mass, so in terms of how much energy it has per unit mass, or how much energy it has per unit volume. The discharge curve looks something like this, and this would be different for different types of battery, but this is how much voltage it has compared to how much energy it has got left in it. So as you deplete the energy in the battery, the voltage will slowly drop, and when you got rid of all the energy, when you've used all the energy up, then the voltage will drop very low. The cutoff voltage is the voltage at which essentially the battery doesn't become useful anymore. So if there's a certain voltage you require from this battery, so it might be this voltage here, then the cutoff voltage corresponds to this point, this voltage level. If you're talking about in terms of energy getting from the battery, so for example the 95% energy mark, so this might be this much energy here, then this would be your cutoff voltage. The open circuit voltage is just when you do not have anything connected to the battery and you measure the voltage across it. The closed circuit voltage is when you put on a specific load across that battery and then measure the voltage. The midpoint voltage is when the battery is 50% discharged. So at the 50% level discharge, this is your midpoint voltage. Self-discharge. So if we go back to our picture of a battery, then these chemical reactions, if you have a load present, then this forces the chemical reaction because the electrons flow through this route. If there's nothing connected here, so we take that out, you would hope things just sit as they are until you connect something. However, in practice, there are reactions going on, and this effectively discharges the battery over time. So self-discharge is when these chemical reactions are occurring when there's nothing connected, and that essentially is losing energy out of the battery. An internal resistance is essentially how hard it is for these ions to flow within the battery. And then this limits the actual amount of current you can draw from the battery. If the resistance is high, then the battery will start to overheat. So internal resistance ultimately results in the C rate of the battery. Primary batteries are your single-use batteries, so they are the non-rechargeable type. You only get to use them once. They're low cost and they provide high energy density, and therefore they are compact batteries. There's a range of primary type batteries out there, depending on the materials. The most commonest one being the alkaline type. But as you can see, depending on the materials, you can get to really high energy densities from these. And depending on battery type, they've got various applications. Your secondary cells or secondary batteries are your rechargeables. And these work by, once you have used them, you can connect them up to charge, and this reverses the chemical reaction that has taken place, so you can use them again. The recharging process is not 100% efficient, and therefore they do have a limited lifetime, typically between 100 and 1,000 recharges. In terms of the materials used for this, probably the most commonest type is your lead acid or sealed lead acid, and this is used in cars. These are very cheap, but in terms of energy density, they're very poor. And then you move on to the more specialist type like lithium ion, etc., lithium polymer, which provide a lot better energy densities, but at the higher price. To charge secondary batteries, the safest way is what's called trickle charge. And what you have is a constant voltage across the battery at a very low current. So it's the safest way, but it does take a long time. When you're fast charging, depends on the battery type, but for the lead acid and the lithium ion, what you do is you charge at a constant current. So you're on this part of the curve, and you're putting a constant current into the battery, and what you'll see is the voltage increase on the battery. When the voltage gets to a certain value, then depending on the battery type, you can either keep the voltage constant and trickle charge, which is what you do for your lead acid type, or in the case of lithium ion, then no further charging is required. You do have to be careful with charging, because if you charge things too rapidly, then the battery can overheat and explode. For the nickel cadmium nickel metal hydride, it's a similar scenario. You charge with a constant current of a C rate of about 1, and then you monitor the characteristics of the battery. So when they are fully charged, you notice a slight dip in the voltage, and you also notice a rapid increase in the temperature. So it's very important to stop at that time, again, before they overheat and explode. So when you're charging secondary batteries, you do have to be very careful in this process, because there is the risk of explosion. When you come to use batteries, a couple of things to consider. As I said, high currents are dangerous. You have to use them within their specification. And the best way to ensure that is to put a fuse in series. So a fuse is a thin piece of metal that if you pass too much current through it, it overheats, melts, and then breaks the contact. So you can get fuses for different current ratings. So it's good practice to put a fuse in series with any battery, and then that will stop these high currents overheating and then the risk of explosion. In terms of choosing batteries for your application, we did have lots of options to choose from. So we've got these. So some of them are very good high energy density, but there's also issues of being able to source the material, and then what do you do when the battery is finished? So for example, these are toxic and corrosive. So when you're doing your projects and you're only making one item, then this is not really a concern. But when you are making, if you went into mass production and you were making millions of this product, then potentially you're going to have a lot of toxic chemicals as a byproduct when the product comes to the end of its life. So that is something you should consider when you're actually designing these things. When you're designing your systems, what materials, batteries, etc. to use. So that concludes our discussion on batteries. In the last tutorial of today, we'll look at some good practices when you come to design your circuits.